Well, hi everybody. In this lesson we're going to work with ratios and proportions. That's going to give us the mathematical foundation we need to start working with gear ratios and torque and horsepower. We'll do that in the next lesson. Um, if you think about ratios, they're all over the place. In the automotive and heavy equipment industries, there's tons of different kinds of ratios that you've come across and will come across. I've got a couple of them right here, like a two-cycle oil. You have a two-cycle engine, the oil and gas need to be mixed in the right ratio so that it doesn't have too much or too little oil in it. And transmission, gear ratios, all over the place. Depending on whether you want a higher torque or a higher RPM, those gears need to be designed to give you the right ratio. Compression ratios, air to fuel ratios, front to rear weight distribution ratios, they're all over the place. So that's what we're going to work with. By the time you're done with this lesson, you're going to be able to write ratios in all the different ways that are equivalent, and you'll be able to express ratios in lowest terms and as unit rates. So let's get started. So first of all, there's three different ways to write ratios, and the example I'm going to use so we have something to work with is that two-cycle oil and gas ratio. Most engines require that you mix about 2 gallons of gasoline for every 8 ounces of two-cycle oil, and that depends on the type of oil, but that's a pretty common ratio. So here's the first way you can write that. You can literally just use the word two and say 2 gallons to 8 ounces. Okay, that's the way that we say it. Usually when you write it, you don't use the word two. We use a colon, 2 gallons, colon, 8 ounces, means the exact same thing. And the third way that we're going to use the most is actually to take that ratio and express it as a fraction, because then it acts and behaves with many of the same characteristics as a fraction. We could say 2 gallons over 8 ounces. So there's two main types of ratios, and the first one is this, writing a ratio in lowest terms. Let's write the ratio 2 gallons to 8 ounces in lowest terms. What we want to do is start by writing our ratio 2 gallons to 8 ounces as a fraction. Now, can you reduce that fraction? You bet you can. You can divide top and bottom by 2, and you can write that in reduced form as 1 gallon. But if you're only going to mix 1 gallon of gasoline, then of course you'd only need 4 ounces of two-cycle oil. Now we've gone to lower terms here, but we can actually go lower. And the reason that we can go lower is we know, and this is from your conversion sheet, that 1 gallon is 128 ounces. And so we can take that gallon in the top, and since the units don't match, we can rewrite it so that they do match. We can say we need 128 ounces of gasoline for every 4 ounces of oil. And we did that because we want to make the units in a ratio match if it's possible. Now, can we reduce 128 ounces over 4 ounces? We can, and just like we've seen a few times now, the units of ounces cancel, so we really just have 128 over 4 with no units of all. So we really just have 128 over 4 with no units at all. But 128 over 4, those both reduce. They both divide by 4. And if you do that, we end up with 32 over 1. Or as we know, we can express that using a colon. We would say 32 to 1. And that is the gas to oil ratio. That's in lowest terms. Both of these are acceptable, 32 over 1 or 32 to 1. They mean the exact same thing. We could even use that third method and say 32 to 1. Those are all equivalent to lowest terms. So let's take a look at a couple more examples here. Let's write the ratio 4.35 to 2.1 in lowest terms. Well, again, we start by taking 4.35 and putting it over 2.1. Write it as a fraction. Now, this ratio has decimals in it, and we don't like that. We're going to see that when we're working with gear ratios in our next lesson as well. We can move that decimal anywhere we want as long as we move top and bottom by the same distance. So in the top one, we need to go 2 places to the right to get rid of the decimal. That becomes 435. The bottom also then has to go 2 places. And so our new ratio becomes 435 over 210. Now that's the exact same ratio, but this one's decimal free. Now those both reduce, And in fact, you can divide both of those by 5. And if you'll do that, you end up with 87 over 42. But that's not lowest terms either, because those both divide by 3. And when you do that, you end up with 29 over 14. Those don't reduce anymore, and so that is lowest terms. Now here's the thing. There's a temptation to say, oh, 29 is over 14. That's improper. We could call this 2 and 1/14. But remember, this isn't a fraction, so it wouldn't make any sense to turn it into a mixed number. This is a ratio. It just looks and acts a lot like a fraction, so we would stop right there. We could say 29 to 14, or we could say 29 to 14, and all of those are equivalent. Our second one, 1 foot to 1/4 inch. Okay, let's get this into lowest terms. 1 foot to 1/4 inch, those units don't match, but we can make them match. Just like we turned gallons into ounces in the last example, we know that 1 foot is 12 inches, so we can say that that is 12 inches over 1/4 inch. There, our units match, those are gone, so now we have 12 over 1/4. But that's the same as 12 over 0.25, and here again now we have a decimal. We don't like that, so let's move that 2 places to the right, 2 places to the right, and that becomes 1200 over 25. But those both divide by 25, and if you do that you end up with 48 over 1, and that is lowest terms, 48 to 1. And that's the scale of most architectural blueprints for houses. They use 1 foot of actual house is represented by 1/4 inch on the blueprint, or in other words, it's a 48 to 1 scale. The real house is 48 times as big as the blueprint is. And let's do one more. 240 people to 18 tables. Now, we can't make these units match. Up here we had feet and inches. We could change feet to inches and make them match, but here we can't. There, you can't convert between people and tables, so the units are just going to stay on there. But we can reduce 240 over 18. Those both certainly reduce. And they both divide by 6. And if we do that, we end up with 40 over 3. Now, since the units didn't cancel, they have to stay on there, so that's 40 people for every 3 tables. There, and we've got that in lowest terms. Okay, I'd like you to take a piece of scratch paper and do the 3 on your screen, and unpause the video when you're ready to see the solutions for these 3. Okay, our top one, 38 centimeters to 12 centimeters. The units there match, they cancel off, so it's really just 38 over 12. But those both divide with a common factor of 2, and so we end up with 19 over 6, and that's it. That's in lowest terms. You don't have to express your answer all 3 ways. I'm just noting that those are all equivalent. Next one, 8.75 gallons over 1.5 gallons. The units match, so they cancel off right away, and we have 8.75 over 1.5. But we could move the decimal 2 to the right to get rid of the decimal point in both numbers, and that becomes 875 over 150. Now those will both reduce down. They both divide by a common factor of 25. And if you do that, you end up with 35 over 6. That is lowest terms. And our last one, 10 feet to 75 inches. First of all, that does reduce down a little bit. Those both divide by a common factor of 5, and so we could say that that is 2 feet over 15 inches. Now, feet and inches can be made to match. Let's change the top. 2 feet. Well, 1 foot is 12, so we could say that 2 feet, that is 24 inches over 15 inches. By making the units match, they cancel, and we're left with 24 over 15. But they both divide by a common factor of 3, and we end up with 8 over 5, and that is lowest terms. And we're done. Now that's all well and good, but suppose you got a job and you made $33 in 4 hours. $33 in 4 hours. That's already in lowest terms. So if somebody says, "Hey, how much do they pay you?" You wouldn't say, "Oh, I make $33 in 4 hours." That's lowest terms, but it doesn't make sense. Of course, you know what you would do is you would just divide that out. You would treat that fraction bar as a division sign. And so if we take $33 and just divide it by 4 hours, we end up with $8.25 per hour. That's also a ratio, but we call that a rate. Rates are easy. Rates are nice because all you do is reach for your calculator and divide the two numbers. Now, notice that the units stayed. They didn't cancel off, and so both of these units stay, and we have $8.25 for each hour. Okay, the second one that's here, if you drive 243 miles and you use 13.6 gallons of gas, we could put that in lowest terms, but that's a lot of work. Instead, we'll just divide that out. 243 miles divided by 13.6 gallons. If you divide that, you get 17.9. But what are the units on that? Well, they didn't cancel, so they're still there. We would say 17.9 miles per gallon. And that's it. And again, that's a rate or a unit rate. Anytime you use the word per, you're talking about a unit rate. Dollars per hour, miles per gallon, unit rate. So I want to really emphasize the difference here. When you write a ratio in lowest terms, it's still going to be a fraction. Units sometimes cancel, but you're still going to have a fraction when it's in lowest terms. But a rate, when you're asked to compute a rate, then you just reach for your calculator, divide it, and round it off. So water weighs about 25 pounds for every 3 gallons. That's how you'd express that weight in lowest terms. But as a rate, you would just say it's about 8 1/3 or 8.33 pounds per gallon. Okay, so here's an example. The original Model T was rated for 20 horsepower in 1903. It had a 177 cubic inch engine. The question is, what is this ratio as a rate? Well, that means that we can take 20 horsepower over 177 cubic inches. And if you divide 20 by 177, you'll get 0.11 horsepower out of each cubic inch. That was one early way to measure engine efficiency, 0.11 horsepower per cubic inch of engine displacement. Now, of course, with engine technology, that got better and better. And the 1965 Chevelle created 350 horsepower, and it did that using 327 cubic inches. So if we turn that into a rate, you end up with about 1.07 horsepower per cubic inch. And in fact, with turbochargers and mini valves per cylinder, this number can go up over 2 or 3 horsepower per cubic inch for some really high performance engines. Okay, I want you to do this problem. This is a quick one. Grab your calculator. If you've got a chain that weighs 35 pounds and it's 14.5 feet long, express that ratio as a rate. And then unpause to see if your rate is correct. All right, pretty straightforward. If you have a 35-pound chain that weighs 14.5 feet, you could divide that and you get about 2.4 or 2.41. And since the units didn't cancel, that's pounds per foot. So it tells you how heavy the chain is, 2.4 pounds for each foot of chain. Now you could say, wait a minute, how do we know that the 35 was first? Why couldn't we take 14.5 feet and divide it by 35 pounds? Well, you could, but you would get different information. If you divide it the other way, you get 0.41 feet per pound. And that's also unit rate. But it tells you that it takes a little bit less than half a foot of chain to weigh 1 pound, whereas this method tells you that you've got 2.4 pounds for each foot of chain. Same information, but expressed differently. So which one is right? Well, they're both right, but if the chain weighs 35 pounds and is 14.5 feet long, we would usually assume that the first piece of information is the one that goes on top, and that's divided by the second piece of information, and that's typically how we'll work with unit rates. Okay, that leads us to our last topic here, a proportion. When you have two ratios that are known to be the same, then you get a proportion. Here's a simple example of that. A full 250-foot roll of steel weighs about 46.5 pounds. That's a ratio. We can say 250 feet weighs 46.5 pounds. A partial roll weighs 31.25 pounds. Now, we know the ratio between feet and pounds has to be the same. So that has to be equal to a partial roll that weighs 31.25 pounds. Now, since we're putting pounds in the bottom in the first ratio, we should put the pounds in the bottom on the second. So 31.25 goes in the bottom right. And that means the top number must be in feet. And that's what we're trying to find. If 250 feet weighs 46.5 pounds, then how many feet are there if it only weighs 31.25 pounds? Definitely less than 250, right? It doesn't weigh as much. There's not as much cable. We're ignoring the weight of the spool because compared to the weight of that steel cable, that wooden spool doesn't weigh very much. Now, here's the key. We can find this number by cross multiplying. If we multiply these two numbers together, we have to get the same thing as if we multiply these two numbers together. So 250 times 31.25, and we get 781.25. In the other direction, it's 46.5 times something we don't know. Now to figure out what that unknown number is, we'll divide off the 46.5. And our unknown number on the top right turns out to be 168.0. And since it was in feet, the cable on the roll must be about 168 feet. So the thing I want you to recognize here is when you have a proportion to solve, two numbers diagonally will be given and then one won't. We can multiply the two that we know diagonally and divide off the third. That was 250 times 31.25 and divided by 46.5, and that leaves us with our unknown value in the proportion. Okay, this is how battery warranties work actually. They're called prorated warranties because they're based on a proportion. A battery with an 84-month warranty was purchased for $88.99 in March of 2018, and it failed. So if that battery goes back, you won't get a full replacement. Depending on the warranty, you'll get a prorated replacement. Here's how this works. We know that if you spend $88.99 on this battery, it should last 84 months. The problem is our battery didn't last 84 months. It only lasted from March of 2018 until September of 2020. So how many months did it last? Let's count that up. From March of 2018, the last time we were in March was March of 2020. And of course, March of 2018 to March of 2020, that's 2 years, which is the same as 24 months. But then from March of 2020 until the time it died, which is September of 2020, well, March is the 3rd month, September is the 9th month, that's another 6 months. And so we can conclude this battery lasted 30 months. 2 years, 6 months is 24 plus 6, 30 months old. So let's go back to our problem. The battery should have lasted 84 months. If it only lasted 30 months, we're going to put months on the bottom since we put it on the bottom originally, then how much was that battery actually worth? It sure wasn't worth the $88.99 that we spent for it. Let's figure out what the value of that battery is. So again, we're going to take our calculator, $88.99 times 30 divided by 84. And we end up with $31.78. We're rounding to the nearest penny. Now the thing is, that doesn't answer our question. $31.78 is what this bad battery was worth. In other words, we used up $31.78 of its value already. We're not going to get that back. So our refund will be $88.99. That's how much we paid, but we did use $31.78. And if we subtract that, we're going to get back $57.21 towards a new one, because that's how much more value we should have gotten out of that battery. Okay, here's a similar problem. Tires are also warranted in this way. So if you have a tire with a 55,000 mile warranty and it's $126.49, but after 46,500 miles it's shot or defective, then how much credit should you get back? Well, this is very similar. Instead of months, we're counting miles. See if you can set that up and unpause when you're ready to see the solution. Okay, we're going to set this up using a proportion again. We know that if we spend $126.49, that tire should last 55,000 miles. But that's for a good tire. A junk tire only lasted 46,500 miles. That means it's not worth $126. The question is, how much is it worth? So we'll cross multiply 126.49 times 46,500 divided by 55,000, and we end up with 106.94. Now that's not how much we get back, that's how much of the tire's life we used up, which makes sense because we got most of the tire's life out of it. We got most of our $126. So to find the amount of the refund, or credit towards a new tire more likely, we'll take 126.49 and we're going to subtract off 106.94, and we're left with $19.55, which might not seem like much, but that's probably one of a set of 4 tires, and that's worth making a claim on. Okay, so that wraps up this topic. We did a couple of things in this lesson. First of all, you noted that there's 3 different equivalent ways to express a ratio. You know that you can take a ratio and write it either in lowest terms, that is to say treat it like a fraction, or you can just reach for your calculator and divide it out to get it in decimal form, and we call that a rate. Make sure to always keep your units on rates. Rates are meaningless if they don't have the units associated with them. And we solved some proportions and a couple of simple places where proportions are used. So that's it. Make sure to rewatch anything that gave you trouble there. Otherwise, we're going to move on and apply these topics to gears, torque, and horsepower in our next lesson. We'll see you then.